Hello everyone and welcome to the Game Engine programming series where we write a game engine from scratch. Today we go back to our D3D12 low-level renderer and create an upload mechanism that uses a copy queue to transfer resources to the GPU. If you are watching this video in the directx 12 playlist on this channel and wonder why there is a gap in episode numbers, don't worry, you didn't miss anything related to directx. I just took a break to add a content browser, write an FBX file importer and a model viewer to show the imported models as you see here. So today will be a continuation of directx episodes. Before we start, I would like to add an assertion that would give a compile time error if the template type t here is not a primitive type, such as int, float, or a boolean. Right now I can call this function with a string, which wouldn't result in anything good. Fortunately, there is a way to find out if a type is a primitive type. We can use standard is arithmetic to assert that t is one of these types. Otherwise, the assertion will cause a compilation error. Let's add the same assertion to the read function as well. Next is a fix for the FBX importer, where we import tangent vectors. Here I normalize the tangents before transforming them, which is obviously wrong. I also believe that I need to use the original transform matrix for this, instead of the inverse transpose matrix. I'm still not 100% sure, so I'll leave this comment here. With that out of the way, we can finally resume our directx programming. Since we got ourselves perfectly packed shiny little vertices in the geometry assets, I think the next step would be to have a way to take those sweet juicy vertices and feed them to the GPU. Feeding resources to GPU using any of the modern graphics APIs is not exactly trivial and needs a bit of explanation. In general, a system with a discrete graphics adapter has three memory types. Most, if not all, GPUs have dedicated GPU memory that's only accessible by the GPU. Often there is some memory shared between the CPU and GPU. This can be memory on the GPU or the system memory. Some systems with integrated GPUs have only shared memory and system memory. Finally, there is the good old system memory which we all know and love. From GPU's point of view, the GPU dedicated memory, which is often located close to the GPU, is the fastest to access. Shared memory is sometimes just a virtual memory mapping from the system memory to GPU address space and is therefore significantly slower for the GPU. When we create a resource, it will be created in one of these regions, although I'm not sure if a resource can be created directly in the system memory. Anyway, the GPU-only resources are the fastest for GPU processing and should be preferred for any resource that's not going to be updated by the application. The CPU-accessible resources are slower to process and are mostly only used for a small set of data that needs to be updated for each frame. But wait, if the GPU-only resources can only be accessed by the GPU, how do we initialize them with any data to begin with? Well, we need to do it in three steps. First, we create a CPU-accessible resource and write the data to it. Then we create a GPU-only resource and use a command to copy the contents of the first resource into the new one. Finally, we release the first buffer. The CPU-accessible buffer is called the upload buffer because it's used to upload data to GPU. As I mentioned, we have a command that does the copying, and we need to use a command list to record that command. Remember that commands are first recorded and then executed using a command queue. We already use a command queue to execute the graphics commands, but we don't want to bother our rendering pipeline with copy commands. I also want to be able to load the assets asynchronously, and that means that we are going to use multiple threads. Let me introduce you to GPU engines. To directly quote from this documentation, most modern GPUs contain multiple independent engines that provide specialized functionality. Many have one or more dedicated copy engines and a compute engine, usually distinct from the 3D engine. Each of these engines can execute commands in parallel with each other. Direct3D12 provides fine-grained access to the 3D compute and copy engines using queues and command lists. End quote. You can check if your graphics adapter has any of those engines by running Windows Task Manager, select Performance, and choose GPU. As you can see, there is a 3D engine and a copy engine on my GPU. You can also see the amount of dedicated and shared memory for graphics resources. If you open the drop-down menu next to any of these graphs, you can see that there are multiple engines for each type. So the idea is to use a separate command queue with the specific task of executing copy commands. That way we don't have to execute those on the 3D queue. We also don't need to do any synchronization between 3D and copy engines, because we only use the resources when they are fully initialized and ready for use. In this video, we'll mostly be working on setting up the copy command queue and something that I call an upload context. To get our feet wet, let's see how we can create a CPU accessible resource to which we can write some data. We can write a helper function that creates buffers with different usages. I'll add this function to the helpers so we can use it where needed. Here we define a createBuffer function which returns an ID3D12 resource interface pointer. The first parameter is a pointer to the initial data that we would like to be contained in the buffer. This can be a null pointer if we just want an empty buffer to be created. The second parameter is the buffer size. Obviously, this size needs to be non-zero. Because most of the time we only use the first two parameters, I'll make the rest of parameters optional with a default value. With the next parameter, we can specify if the buffer should be accessible by the CPU so that it can be updated after it was initialized. Next is the initial state in which the buffer resource should be created. We can also set resource flags if needed. If we provide this function with a resource heap, it will create a placed resource instead of a committed resource. For placed resources, we can provide a heap offset where the buffer resource should be placed within the heap. This is one of my favorite helper functions because it does so many things, and yet, as you will see shortly, it's not that complicated. Okay, let's write the implementation. Since this pointer to data is also optional, I can make it an optional parameter altogether. In order to create a resource, we need to fill in a resource description. We have done this before to create texture resources, but this time we need to fill it in for a buffer resource. So the resource dimension is a D3D12 resource dimension buffer, and the alignment is 0, so the driver will create the resource at the proper alignment for us. Since a buffer is treated as a one-dimensional array of bytes, we set the width of the resource to be the length of the array, and the height should be 1. Obviously, the depth and mid-level values are also 1 for a one-dimensional array. How the data in the buffer is interpreted is determined later in our C++ code or in the shader, so the format is not known at this point. According to the documentation, sample description must be set to 1,0 for buffer resources. The layout is row major, which makes sense because a buffer is a row of data. If we need to be able to write to this buffer later, we can't set any flags. Otherwise, we can set the flags as provided in the function parameters, although our choices are quite limited. In fact, we can only use allow unordered access flag when the buffer is not CPU accessible. If the buffer is CPU accessible, the state is always generic read. Otherwise, we can use the state as given in the parameters. As I mentioned, if we are given an interface pointer to an id3d12 heap, we are going to create a placed resource. Therefore, we can simply call create placed resource using the heap pointer, heap offset, resource description, and resource state. If the function succeeds, it will write the resulting pointer into our local resource pointer variable. If we don't have a pointer to a heap, we'll create a committed resource. Calling create committed resource will implicitly create a heap and place the resource in that heap. Therefore, we need to tell this function what kind of heap it should create by providing it with the heap properties. If you would like to write to this buffer, like we do with constant buffers for example, we need to use the upload heap properties. Otherwise, we use the default heap properties. Of course, we haven't defined the upload heap properties yet, so let's do that now. Here we just copy the default heap properties and simply change the heap type to upload, and we are done. That's it for creating the buffer resource. Now we need to initialize it with the data, if any. Depending on whether this buffer is CPU accessible or not, we use two different methods to write to this buffer. Let me also change this parameter name to is CPU accessible. So if the buffer is CPU accessible, that means that we can write to the buffer at any time. Therefore, we can ask directx to map the memory of the buffer to system memory, where we can simply write to it. If this was a buffer that we would like to keep writing to, we could leave it mapped to system memory and keep the buffer's CPU address around for writing. In this case, because we are just initializing the buffer, we unmap it. Reading from this memory can have performance penalties, so we need to be careful that we don't accidentally read from the buffer. There is no way of ensuring that using directx API without building extra layers of abstraction. Now, if we need to initialize a resource that's accessed only by the GPU, we need an upload context that creates an upload resource first and then copies the resource to the GPU-only resource. Let's create the upload context. I'll add a new header file and call it d3d12 upload.h. This is a low-level renderer submodule, and therefore we need to have the usual initialize and shutdown functions. Next, I'll create the class declaration for d3d12 upload context. It's again one of those classes that can't be moved or copied. The constructor will create a CPU accessible upload buffer to which we can write the buffer data using its CPU address. Then we copy this upload buffer to another resource which is only GPU accessible. To copy a resource, we need to record a command using a command list, which will be executed when we call endUpload function. That's why we also have a pointer to a command list here. We can upload multiple buffers in parallel. The frame index is the index of each upload. Finally, I add a couple of accessor functions. Going back to create buffer function, we can use the upload context to copy our data to the upload context's upload buffer, and then copy the upload buffer to the GPU-only buffer resource. When all is said and done, we return the buffer resource. To summarize, first we create a buffer resource using a resource description. The resource is either placed in a heap if the caller provided a heap pointer, or it will be created as a committed resource using an implicit heap. If the buffer needs to be initialized with data and is CPU accessible, we simply map it to system memory and write the data. If it's not CPU accessible, we use the upload context to copy the upload buffer to the GPU-only buffer. To copy resources, we can use the command queue in core.cpp, but that could potentially have a negative effect on the frame rate, because we would have to wait for copy commands to be executed. That's why I'm going to create a simplified version of the 3D12 command class that is dedicated to copying resources. Because it's rather similar to this class, I won't spend a lot of time explaining the CPU-GPU synchronization, as I already did that in these videos. First, I define a constant for the number of uploads that can happen in parallel. I choose 4, but it can be any number. It simply defines how many threads can record copy commands at the same time. As I said, we use a dedicated command queue to copy resources, which has its own synchronization stuff, like a fence, fence value, and fence event. Similar to core.cpp, we also need a command frame, which can be used to wait for the command list to be executed. This time I'll call it an upload frame, but it's essentially the same thing. The main difference is that we now have a command list per frame, because we can use multiple threads, and each thread needs its own command list. In addition, it also contains the upload buffer's CPU address. We also have a function that waits for the command queue to execute the command list and resets the frame so it can be used for the next upload. The release function waits for the command queue and releases the command allocator and command list. We can know when the command list has been executed by checking if upload buffer is a null pointer. I'll add an array of these upload frames. Each thread can pick a frame that's ready and use it for upload. Now let's implement the wait and reset function. It's pretty much the same as this function, except it also releases the upload buffer and resets the CPU address. So we check if the completed value is less than the fence value, which would mean that the command list has not been executed and we need to wait until it's done. After copy command execution, we don't need the upload buffer and we can release it. That's also how we can infer if the frame is ready for upload in this function. Let's write the initialize and shutdown functions next. For each upload frame, we need to create a command allocator and a command list. Note that this time we are using a command list type copy for the command list type. This is to let the API know that we would like to use the copy engine to execute command lists. We also give each command allocator and command list a name for debugging purposes. Before creating the command queue, we need to fill in a description of what kind of command queue we need. In this case, we again specify command list type copy in order to create a copy queue. And then we can call create command queue using this description and give the resulting command queue a name as well. Next, we create the fence and give it a name, and finally we create the fence event. When shutting down, we release all upload frames, the fence event, command queue, and the fence. We also reset the fence value to 0. Let me also properly handle the case where the fence event creation failed. I don't know why it would ever fail, but if it did, we would hopefully not crash. And I'll do the same in core.cpp. This is the end of today's video. Although we still need to implement the upload context constructor and end upload function in order to finish resource upload. We'll start with that in the second part of this episode. I'll also write a function that uploads the mesh data to the GPU. Thank you so much for joining me, and I'll see you next time. Thanks for watching. If you like this video, please feel free to like and subscribe. If you join me on Patreon, you'll get access to the code on GitHub, so you don't have to type everything over from the video. Plus, there are also other nice goodies and rewards exclusive to my Patreon supporters. Please use the link in the video description to check them out. I hope to see you next time. Until then, take care and happy game engineering!